Wow, what a crowd. Good to be back in person. So thank you for being with us today, online and on-site. Today is the first time with the majority on-site, which is really great. I'm delighted to welcome Professor Maryam Kamgarpour. Maryam is a Tenure Track Assistant Professor here at EPFL. The title of the talk is Learning for Safety and Coordination Uncertain Dynamical Systems. Sorry for that. You know how it works. So we have 45 to 50 minutes of talk normally, and then we have time for questions at the end. Maryam agreed, if you have urgent questions, shoot them right away. Same for people online. And otherwise, keep them for the 10-15 minutes of Q&A we have at the end of the talk. Without further ado, screen is all yours.
Thank you.
You're welcome.
So, hello, everyone. Thank you, Jan, for organizing the talk and for the invitation. So it's my pleasure to be here with you and telling you a little bit about my research and hopefully get to meet some of my neighbors. So the title is Learning for Safety and Coordination. Okay. So my research is on a control theory, which is about decision-making in environments that are dynamic. In other words, they're changing and are uncertain. And whereas we started using control to help us for simple and repetitive tasks, such as control of a turbine, a speed control in a turbine, or a cruise control in a car, or a robot that can clean our floor, we are using control in increasingly complex, uncertain domains. For example, we have an integrated smart power system where we are controlling a large number of producers and consumers to balance the supply and demand of electricity at each time and ensure a stable power grid. We are going to an intelligent transportation system where autonomous cars are being driven alongside human-driven cars. And we are also coordinating the scheduling of various modes of transportation to ensure safety and efficiency. And from simple robots that help us in repetitive tasks, we're going to robots that help us in complex, dangerous tasks. Okay. So as we increase the automation in our societies, our autonomous systems have to work under increased uncertainty. And my research focus is on developing algorithms that guarantee system safety and coordinate the interactions. So in this talk, I'm going to talk about my work on safe learning and control, and I will talk about my work on multi-agent learning and control. So let's get started with an example. So here's an example of safe control in autonomous driving. So we have a dynamical system, which is the autonomous car and the nearby traffic. Our objective is to plan a safe maneuver for the car, and our control inputs are the car velocity and steering angle. The challenge is uncertainties in nearby cars' intents and trajectories. So here, from the perspective of autonomous car, it's seeing the environment with these sensors, and we can use the state-of-the-art trajectory prediction algorithms built on, for example, deep neural networks. And you can see that, so here you see the trajectory predictions for cars at an intersection, and you see as the horizon goes on, the predictions become increasingly uncertain. So how can we plan a safe maneuver despite these uncertainties? Let me briefly tell you about the formulation of this problem. So we have an objective function J, which would be the progress of the car on the road, reaching some goal set, and we have a constraint. And our control input here is shown with A. So we want to minimize a cost function subject to the constraints. Okay. The challenge, one of the challenges with this problem is that the constraints depend on a parameter denoting the uncertainty. So in a car example, this could be the trajectory of the nearby cars. We don't know these trajectories precisely in the time that we are planning, but we might have data available about this. So over the past few years with my students and collaborators, we have been working on developing a framework to address this stochastic optimization algorithm. And one of those frameworks is by satisfying a probabilistic safety. So we say that given that we don't know what the uncertainty is, we assume that we have data samples of the distribution of the uncertainty. And then we say that we want to satisfy the constraints with high probability. So probability of violating the constraints should be less than or equal to arbitrary small epsilon threshold. Okay. And we have been working on developing tractable algorithms for solving this class of problems and using them in a control application in closed loop. Let me just show you one simulation. Here, the problem we formulated for trajectory planning of autonomous cars was cast as a data-driven mixed integer stochastic optimization problem, which we developed algorithms to solve it. And we applied it to the new SIM data set, which is an autonomous driving data set, and with state-of-the-art trajectory prediction algorithm, Trajectron++. And here you see an intersection exactly coming from this data set. This is a car that we're trying to control in purple. These are two cars in the nearby traffic, and our control car wants to maximize forward progress and go straight, but these nearby cars have uncertain trajectory. So we can formulate this problem as a stochastic optimization and apply our algorithm and replan every 1 second where we have updated information about the trajectories. And here you see the trajectory forecasts that are quite uncertain. So this was for the red car coming from here, and this is for the green car. And this is just two time seconds ahead. We see the uncertainty, possible sandbox, the state-of-the-art trajectory prediction. And so we plan our trajectory to cross the intersection safely without colliding with any of these nearby cars. And here, these refer to different ways to formulate and solve the problem based on how we handle uncertainty. So moment trust approach, moment robust approach, conditional value at risk, and conditional value at risk robustness. They encode different ways of capturing the safety requirements. Okay. So this is just what we mean by safe control and how we can handle uncertainty. Now I want to focus on the most recent line of our work, which is on learning. Okay. So if we look at the evolution of control approaches, we are going from a modeled and optimized approach where we model the car dynamics or robot dynamics, and then we only have some uncertainty, for example, from partial knowledge of environment, to a completely end-to-end learning approach where we apply an input and we have here a black box and we measure an output. Okay, so we model and optimize to just interact and learn the controller directly. What is the motivation? Well, because the systems, as I mentioned, that we are introducing autonomy, they're increasingly more complex. We have more uncertainties. We may not want to deal case by case at a left turn maneuver or a straight forward maneuver at the intersection and so on. We want to have a framework that is flexible to handle all of this. Or in a robotic control case, we might have highly nonlinear dynamics that are anyhow very hard to design and control it. So let's just then, given the success of derivative-free optimization and neural networks, let's go directly for an input-output approach, black box approach. And the question over the past few years I've been focused on is how can we incorporate safety in these model-free learning algorithms? Okay, so we're gonna look at the formulation of this problem. Again, we have a constrained optimization problem. So we want to minimize the cost function J subject to some constraint C. The difference between the past formulation and the current one is that J and C are both unknown. Okay, so we want to minimize an unknown objective under an unknown cost function. And the set of feasible sets is set of A such that CLA greater than or equal to 0, shown here in D, is also unknown. Okay, so how can we approach this problem? So let's look at this problem again. So the challenge, as I said, we want the iterates of our algorithm to be safe. So we apply, what do we know? We don't know J and C, but what do we know? We can apply an input AT and we can measure J and we can measure C. Okay, and we want to ensure that the CATs are always greater than or equal to 0, so the iterates are safe. And we want to make sure that eventually we converge to the minima of this objective. So we have possibly noisy function evaluations, the black box information, and we want to design a safe algorithm. So what are existing works to address this problem? It seems quite a fundamental setup. Surprisingly, there's not a lot of past work to look at this problem. The closest we found addresses this problem under a Bayesian prior assumption. So assuming that the cost functions and constraints come from a Bayesian model, they develop algorithms to ensure with high probability of safety and the conversion solution. The challenge with this Bayesian approach is that the number of iterations required to learn an optimal solution scales exponentially with the problem dimension. So we try to use convex optimization tools to improve this dependence and have more computationally efficient algorithms. So I give you an overview of the approach we have. So the idea is that in order to ensure the iterates are safe, so as we are learning the optimal solution, we want to make sure we don't violate any constraints. We design a barrier function, okay? So, and then we estimate the gradients of these unknown barrier function, because remember our cost and constraints are unknown, to go in a direction of a descent. And we take carefully chosen step sizes to make sure that we don't violate the constraints. And I'll go into further details in each of these steps briefly. There's some chat. Okay. Yeah. So for the barrier, we use a log barrier approach. But what this means is that we formulate a problem instead of minimize j greater than equal to 0, minimize j of a minus some eta times log of. And as you approach the boundary of the constraint, so as C of A becomes close to 0, this function approaches infinity, so it basically blows up. So this prevents us from getting too close to the boundary and becoming unsafe. And as eta goes to 0, the approximate solution of this unconstrained optimization goes to the true solution of the original problem. So let's talk about now how to solve this unconstrained optimization problem. So that one basic method for doing unconstrained optimization is gradient descent. So AT plus 1 equals to AT minus some gamma step size, or otherwise referred to as learned rate, G of t, where G is the gradient of your object. Okay. But the issue is we don't have gradients because we don't know J and we don't know C. So we want to use function evaluations to estimate the gradient of the barrier function and compute safe step size. And I briefly talk about this. So to estimate the gradient of the barrier, we can just do finite difference approximation. So we measure our functions J and C at several points around the current point and take the average, and this gives us a good estimate of the gradients, but we can quantify estimation accuracy in terms of the finite difference step that we are choosing and the number of sample points we are using to measure our functions around. Okay. So based on the zero order of black box information, we get first order or gradient information. And then the next step is choosing a safe step size, because our iterates are AT plus 1, AT minus gamma t, and we want to make sure if AT is safe, AT plus 1 will also be safe. And here we make an assumption that our functions are relatively well behaved. So they are Lipschitz continuous, the basic assumption, which means that we bound the growth of the function. So if we have an estimate of the Lipschitz constant, and this is C of x greater than or equal to 0, and this is our current iterate, then we know that as long as our step size is sufficiently small, so the next iterate is within this range, the function will not fall below the 0. So we can choose the step size as a function of the Lipschitz constant to ensure safety. Okay. So putting this together, we come up with a safe black box learning algorithm that we can show that under Lipschitz continuity of the functions and a safe initial point, we have an algorithm whose iterates converge to a point satisfying optimality condition. So in a convex setting, they will go to a minimum of the function. In a non-convex setting, they would satisfy the standard KKT optimality condition. And then all queried points are safe with high probability. Okay. So we have compared this proposed approach with the state-of-the-art Bayesian approaches. We have also applied it to reinforcement learning problems and manufacturing problems. So a standard setup for safe reinforcement learning is what's called a safety gym, which is an open source suite developed by Open Artificial AI. And it's very similar to autonomous driving example. Here we have a robot and it needs to reach a goal set, and there are a bunch of obstacles with unknown locations spread around. And the robot can only get black box information about how far it is towards its goal set and where the obstacles are. So we apply our framework and compare it with other RL approaches to show that it can increase the safety as we are learning. So the learning can be online and it can improve safety, meaning not hit as many obstacles as you're trying to find a way. I also collaborated with colleagues in the manufacturing and materials department to apply this framework to building materials where the partial differential equations describing the process involved are so complex that you would like to possibly use black box approaches in order to find a locally optimal solution. Okay, and I'm happy to talk more about these if it's of any interest to you. I just want to kind of summarize this part of the talk, which is on safe learning and control. So I mentioned that the problem of safety can be cast as a constraint optimization under uncertainty. Okay, and we looked at few ways to handle this uncertainty, whether we have a gray box, so we know something about the functions, but just don't know the environment, or whether we have black box where we don't know anything about the functions. And then currently we are working on ways to relax the assumptions, such as knowing the Lipschitz constant or knowing a safe initial point. And on the other hand, exploiting some prior knowledge, such as the fact that we have a dynamical system with partial knowledge about it. And it's a reinforcement learning, which is a repeated optimization setup in order to make the algorithms more tractable in real time. And the sort of eventual goal is that we can have a safe approach. So even when we have an end-to-end learning, for example, an autonomous driving application with neural networks, we can verify that our approach is safe, and with high probability, we will not have collision. I just pause and see if there are questions about this part. Yes.
Yes, so I have a question. So first of all, so when we are approximating the gradient, and you need some samples, right? So
yes.
Do we have any upper bound number of samples that we can say, okay, now this gradient is almost close to the true one?
Yes, yes, you can characterize that. So for a given accuracy, you can bound the number of sample points you can use to get that. And also depending on how close you're sampling. So we are sampling the function at j of a plus some eta times the direction.
The next question is how do you sample, like coming from the volume distribution around that point, or will you just like uniform distribution?
Yeah, that's a good question too. At the moment, we just use uniform distribution. So if you're at a given point, you sample from the uniform distribution sphere, uniform distribution on the sphere around that point, and use that to estimate the gradients. But it's worth looking at different approaches to see if one of these sampling methods could give you better, more increased accuracy. So far, we looked at the randomized sampling approach based on uniform distribution. Yeah.
And the last question is about the Lipschitz constant of the constraint.
Yeah.
This where you have this SC function of A, and you said that okay, we will take the step size according to the Lipschitz constant of the constraint.
Yes.
So do we have some knowledge on this?
Yeah, this is a good question. That's why I said it's one of our ongoing work too. So far we assume some upper bound. So you can see here if this is your function, you're getting kind of a very rough estimate, a conservative estimate, because in reality the gradient would be like this. So you're getting a rough estimate. You're saying that okay, the function is changing this fast, whereas it's changing much slower. So if we can online actually improve the estimate of Lipschitz constant, the approach you could possibly converge faster and less, because you can make less conservative steps towards the goal. Other questions? Okay, if there are no other questions, I will move to the next part, which is multi-agent learning and control. Okay, so for the multi-agent systems, these are interacting agents with coupled objectives and constraints. For example, in a smart grid, we have a number of producers and consumers that are interacting by consuming and producing electricity, and we have to control them to ensure that a power grid is always stable. Okay, okay. In an auction, whether it's an internet auction or a power market auction, we have a number of players that are placing bids, and whether their bid gets accepted or not depends on the bids of other players. So their cost is coupled with others' specific costs. Or in a multi-robotics scenario, or in a transportation network, you have here we have drivers that each want to minimize their travel time, but the travel time depends on road congestion, which depends on the decisions of the other road users. Okay. So the question that we are interested to ask and answer here is, how do multi-agent systems learn to make decisions? So let me first formalize the multi-agent problem. We use a game to formalize this. So we have n agents or players. Agent I has an action AI in her action set capital AI, and the joint action of all players is denoted by AI, and a negative I denotes the action of all players except player I. And player I has a cost function, Ji, which is a function of her action and the action of other players. Okay, so this is what makes the problem different than a single optimization. So we don't have a single cost function. We have a cost function for every player, and that cost function depends on players' action and others' players' action. So in general, we don't have a single action profile that minimizes all these functions. We cannot talk about an optimal point, but we can talk about an equilibrium point, such as a Nash equilibrium, which is a joint action profile of our players, such that each player is minimizing her decision variable given fixed action of all other players. Okay. So this is an equilibrium because no player has incentive to unilaterally deviate from her choice. Okay, so let's think about, and again, another example like autonomous driving. So in the past set of slides that I presented, if this was our autonomous car and it is trying to make a turn, it might model all the other cars and uncertain and moving obstacles, basically. Whereas in a multi-agent way of looking at this problem, it thinks that, okay, that other car might actually change its behavior based on what I'm doing. So there is some interaction involved. Okay. So that other car has also a cost function that depends on my action as well. So I can't just think of optimizing my own action because the other car will respond based on my own action. Okay. And here is a depiction of a Nash equilibrium. For example, if you have a two-player zero-sum game, one player is minimizing, the other player is maximizing. This is an equilibrium. There's no notion of an optimal point for both players, but there's an equilibrium in the sense that minimizing player does not want to deviate from this solution. And similarly, the maximizing player does not want to move. Okay. So the problem of learning in games, similar to the black box safe learning problem that I presented to you, is that player I can choose action AI, and she receives a cost function Ji that depends on her action and action of others. So how can the players learn a Nash equilibrium? Okay, so that they are in a stable strategy set, given this black box information. Are there any questions about the setup? Okay. So I'm going to first summarize. Over the past few years, I've been working on developing a framework for this problem under convexity assumption. So let me just first summarize what we know about this. Learning in convex game. So what do we mean by convex game? We mean that AI, the action set of AI, is convex and compact. and her cost function JI is continuously differentiable and is convex in her decision variable. But it doesn't need to be convex in other places. And so what we know about this class of games is that under certain conditions on the gradient of each player's cost with respect to her own decision variable, AI, then convex optimization becomes a strict subset of convex games. So in general, convex games can capture instances that are beyond convex optimization. And as an example, think of the zero-sum game that I mentioned to you. So we have a min-max optimization problem, and generally algorithms such as gradient descent that work for convex optimization do not work for convex games. For example, the gradient descent on a min-max objective, it's been known that it will diverge. But we can design learning algorithms with provable convergence by leveraging this coupling condition between the gradients. And this is called a monotonicity condition, which I'm not going to go into more detail, but I'm happy to talk to you about it. But the summary is that for convex games, because of the recent, a lot of recent research, we have a much better understanding of conditions under which learning algorithms converge. Questions? So I want to focus now for the rest of the talk on our more recent work on non-convex games, because these are a larger modeling class, so they can handle auctions, they can handle transportation networks, and they can also handle adversarial training, so generative adversarial networks. And what we know is that Nash equilibria may not exist, and they're also hard to characterize. Okay. So we cannot talk about learning Nash equilibria because it's even hard to prove existence of them. Or even if we could, characterizing them is difficult. So first we look at what should the players learn then in this setting. So we can make a connection with a famous algorithm which is called banded algorithm. So let me explain that setup to you. So here for reducing clutter, I removed the superindex I from player I's cost. So let's look at player's I's cost function. It's a function of her own action and the action of other players at each time. But because she cannot control the action of other players, from her perspective, this is a time varying function because she can query it at the same point and get different function values. Okay, so it's unknown and time varying. So player I chooses an action, it doesn't know this function, but it receives a cost. For example, in a transportation network, the driver chooses some routes, it doesn't know a priori the choice of other players, but then after the trip is completed, she can measure her travel time. Or in an auction, the player places a bid and she doesn't know the bids of the others or what does the auctioneer has in mind in terms of the minimum bid to accept, but she will receive whether she will receive or not receive the item, so she gets a reward. Okay, and if she repeats this and places the same bid, she may or may not get the same response. Okay, so it's a time varying unknown function when we talk about learning in games. Yes.
Is it totally random somehow, this extra time varying context that you see, or still is affected by the past decision? So
yeah,
it's varying, but even if it's not understanding, there is actually this impact.
Yeah, exactly. That's what I'm going to talk about. Exactly. So in a kind of a classical banded setting, this function can be arbitrarily time varying and random. And what we are going to exploit is to use the fact that this is a game and this function cannot be arbitrarily random. Exactly, I will talk about that. Ask the question again if it's unclear. So in this case, instead of talking about the equilibrium or a single optimizer which may not exist, we can talk about regret, which is defined as sum of the incurred costs, so JT of AIT from T0 to capital T, minus some of the costs played at the best action in hindsight. So AI minimizes this total cost. So had the player known that the cost functions would be JT in advance, she would choose an action that would minimize this sum. So that's what we call best action in hindsight, had we known the sequence of functions a priori. But she didn't know that, and she played actions AIT, so we can minimize her regret for not using this AI. Yes.
So best cost here means, because like even if you know the sequence of what has been done in the past, concept, if you change your action, this will change the optimum again, I would assume. So
Yes.
you get like this feedback.
Exactly.
So is the best here the conversion of this feedback, or like best in like for fixed sequence?
Yeah, so basically, so here we are talking about this action. So had you known this sequence in advance, but the algorithms that have been developed, the function can be adaptive to your past decisions. So they ensure low regret, even this function is adaptive to your past decisions. Yeah, that's a good question. So we call an algorithm no regret if on average this regret is going to 0. So we can say that in a game setting, multi-agent game setting, the players are trying to minimize their regret. And that's sort of a benchmark that has been, we're not the first, of course, to propose it, but has been proposed because we can think of game as a bandit sort of optimization algorithm where you don't know the cost functions. At each time you play an action, a cost function is revealed to you.
So,
Yes.
So in the best process, you also assume the other players' actions A minus I also best?
No, we didn't assume. But you see, this function is time varying.
Yes.
So it depends on others' past actions, and they may be adapted to your past decisions.
Okay.
But they may not be adversary, or because they have their own objectives, but somehow the point is this JT can be adapted to your past decisions because the other players' actions might get adapted to your decisions.
But you assume the first term and second term share the same other player's action, right? What's the
Yeah, when we talk about no regret algorithms, we assume these can be adaptive. So JT can be based on your past decisions changing.
okay?
Yes. Maybe if I hopefully talk about the algorithm, it becomes a little clearer. It's a good point. So no regret algorithms have been proposed in the past for the bandit setting, and they balance exploration, exploitation. So let me give you an insight about them and see how we're going to use them in games. So if player I has a set of actions and the cost is unknown a priori, and it might be adapted to her past played actions, the player starts with putting a probability distribution, so a set of weights that normalize to 1 on her actions. She samples her actions based on this distribution. So this is the exploration. She doesn't play a deterministic policy, but she samples. And then she gets feedback, so she can observe the cost at time t for her played action. And then she updates the probabilities based on the cost. So this is exploitation. Okay. So the analogy is a multi-arm bandit problem where a gambler is facing a number of arms and she doesn't know the reward of them in advance, and she can stick to the arm or action that has given her the maximum reward so far, or she can explore other arms with the hope of possibly getting improved rewards. Okay. So no regret. So this is a general class of algorithms referred to as a multiplicative weight, and they've been used in bandit optimization. Let me summarize what we know about their regret rates. So again, number of actions of players n, number of time steps that we measure regret is t. Under a so-called bandit feedback, meaning that player only receives observation about her played action cost, we know that regret will scale with this order, square root of t n log n. And if she has full information feedback, which means that she can observe the cost for every one of her actions, her regret, the algorithms that this, based on the same principle that I talked about, the multiplicative weight algorithms, the regret goes of the order root t log n. So are there any questions here? I'll just pause about the banded feedback and full feedback. Yes.
You assume that the optimization function on the right is non-noisy.
For now, assume it's no noise. So we observe, we make some measurement and we exactly observe the reward. But we can, yes, it's a good point to incorporate. At least the algorithms I presented, the regret rate is assuming no noise, but the dependence on t and n would be the same, but you have a variance of the noise as a constant also appearing.
And the question is, you need to have a discrete number of actions.
Yes, that's a very good point as well. So this algorithm, this class of algorithms, multiplicative weight, they assume a finite set of actions. So if you have continuous, for example, in a control problem, you would discretize. And this exactly is the issue, that this dependence can be very large because you will have n would be exponential in number of dimensions. So you will get very poor performance. And that's exactly the issue. So here, this is much better because this linear term in n has disappeared. We have log n, and the exponential in dimension would just become a constant d on the dimension. And that's exactly the issue that we wanted to look at. So can we exploit the game structure to improve this rate so that we don't have this linearity in n? But I want to kind of emphasize the difference between banded and full feedback. So again, and contrast with game setting. So in the banded feedback, if suppose you have one objective function, you query it at one point, and you receive the cost for that point. That's banded. A full feedback, you query it at one point, but you receive the cost for all other possible actions. Okay, so you see that you have of order of n more information because you receive the cost for all other actions. So it seems plausible that the regret is scaling better. Okay. Now we want to exploit the game structure to. So in a game, I will actually go back here. Our cost function is artificially time varying. It's actually a single cost function. But because it depends on other players' action that we cannot control, it's time varying. So we want to exploit this fact to try to actually learn this cost function and mimic full information feedback. Because if we can learn the function and if we know our own action, and after players play their action, we can observe that, then we can get full feedback. Is the idea clear? Any questions? Okay, so let's see how we can exploit the game structure. So here, now we look at a Bayesian assumption. So we assume that we have to make some prior, if you want to learn the functions, we have to make some prior assumption about that. And in this line of work, we made the assumption that they come from, they're a sample of a Gaussian process, which is just a stochastic process with some mean and a covariance function. So these are all possible samples. So if you have a zero mean Gaussian process with some covariance function, which measures similarities between the function at nearby points, these three colors could be all samples of the process. But the point is that once we can make measurements about the function, we can update our prior information and form posterior distribution in a very efficient way. So we observe the cost at our played action and other players' actions, which once we play, we will observe them a posteriori. And here I added a noise. We could include a noise here as long as its variance is small. So we make this observation, and then based on this observation, we can come up with an updated mean and a covariance. So if you see this Gaussian process, you make the prior, you make observation here, 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 then the uncertainty in the function is decreasing in the places where you made measurements, the uncertainty is very small. In the places, because the covariance captures similarities to nearby points, the uncertainty here and here are also small, but away from measured points they're very large. Okay, yeah.
And you said you assume like you have a zero mean prior.
Yeah.
What's the interpretation of that? Why choose zero mean prior?
It's rather arbitrary, just we don't have any knowledge about the function. You can use other priors. Yeah, yeah. Good. Other questions? Okay, and one useful feature of making a probabilistic assumption that we know it comes from a Gaussian distribution is that we can come up with confidence intervals for our estimated functions. So if this is our estimated mean after a number of queries, sigma is our estimated variance, and beta is just a constant we introduce. So mu minus beta sigma, this is a lower bound on the function, on the cost function, and we can choose beta based on the covariance function to ensure with high probability L is a lower bound on the function. So it's called a lower confidence bound. So because we have made, of course, because we made some distributional assumptions, and this distribution has nice analytic forms to do regression with. First of all, we can compute posterior mean and variance, and second, we can have confidence intervals for our estimation. So now what we do is we embed this estimated function to mimic fullback. So recall that the regret algorithms, if you just observe the cost for your played action, the regret grows as poorly with respect to number of actions. But now if you say that actually we are learning the function, so whenever I make an action, I also have an updated estimate of my function, and I use this estimate. I know that with high probability is a good estimate, and I use this embedded in the no regret algorithms. Then we can show that our regret scales much better with respect to number of dimensions. So this is the first term that comes from full feedback, and then there is another term that does not depend on the well, at least doesn't depend linearly on the dimension, but depends on the kernel that you choose. And for general covariance functions, its dependence on T is sublinear. Okay, are there any questions about this? I just will talk about, so we have extended this in several ways. This was actually the main work of one of my PhD students with my collaborators, and this basic setup of using Gaussian process in games to improve the learning rate. We have extended it to several classes of games, like contextual games, where your game depends on some context. For example, in a traffic network, the context could be weather conditions which affect the congestion on the road. To robust optimization, to mechanism design. So here we applied it to balance bike in a bike sharing scenario. Here are the locations where there's a high demand for the bikes, and we looked at how we distribute the bikes around the city to maximize their usage. Okay, based on designing games to have so that the agents can have lower regrets. So they extended the theory and applied it to a few different problems. And I very briefly in the next few moments talk about an application or an extension in theory, which is the most recent, and it's multi-agent reinforcement learning and an application. So this is the latest and the work on this point, where we have not a static game, but a dynamic game. So the game has, so there's a state S of your dynamical system. For example, the environment, this could be in an autonomous driving. The state could capture location of other cars and their position and their velocity. Is a function of the current. The next state is a function of current state and all players' actions. So A1 to AN are the N road users, for example, actions at time horizon H. And the objective of the players depend on SH. and a IH, on the state of the environment and her own action over the horizon. So this is a standard multi-agent reinforcement learning problem. Okay, and we applied the same principle that we used. We learned the function f, which is unknown, from past data. We estimated an optimistic reward. In this case, usually in RL, we use the reward term instead of cost in control. So we made an optimistic estimate of the rewards and embed these in a no-regret algorithm, and we proved that the algorithm converges to a no-regret solution in a scalable way. Are there any questions about this? Okay, I will just show you where an example of where we applied this. So this is more, we applied this framework to a simulation platform called SMART for multi-agent autonomous driving, because it's been increasingly observed that unlike the first part of the talk that I presented to you, where we look at other traffic as moving obstacles, actually it's more beneficial to look at the multi-agent framework to think that there is some coordination in driving and how to use that in our planning. So SMART, they came up with a whole simulation environment that you can embed different learning, reinforcement learning, and Python libraries in it to verify your approach. And they have a bunch of scenarios that are difficult and require coordination, such as U-turn, lane merge, intersection. So we looked at a couple of these scenarios to apply our algorithm, and I will briefly talk about one of them. So here, I'm sorry that we try to get better quality images from this platform, but I will tell you, these are two agents, agent 0 and 1. So this is agent 0, this is agent 1. They're controlled agents. This is a human-driven car. They're trying to both go to this lane. So this agent wants to get to the lane of the human-driven car, and this one just also wants to continue. It's a lane merging scenario, and so if they could coordinate and they could sort of go fast together, they could both overtake the human and gradually do their lane merge. In reality, it's been observed a lot of autonomous cars are very hesitant. They constantly brake because they cannot account for other drivers on the road or possibility of coordination. So we use a multi-agent learning where we train these two agents together. So it's a centralized training, but they get a decentralized policy that they can then implement. And so here we are showing the comparison if we were training each agent individually by looking at the others as sort of moving obstacles. So the average of their rewards and the statistics on the board, versus if we can together coordinate them in a game setting. And so on average, what we observe in this case, and one more case that we looked at in the paper, is that the reward improves when they can coordinate. In terms of the actual experiments that we look at, it means that there's less braking and they coordinate to sort of take over this human-driven car together. Okay. Are there any questions? Yes.
What did you learn exactly? What is the actual space there?
Okay, so we are choosing their speed and steering angle. So that is just that. And the reward for both of them is to maximize progress. And for this one is to also merge to the other lane. So you see, after it overtook, it tries to merge. And I'm sorry about the bad quality of the video. It's worse even here than my computer. So for example, if you're not coordinating with the other, you might be afraid, you're uncertain about what kind of speed they would choose, and you might be very hesitant to make a move. You might let first this guy to pass on, and then you go slowly behind it. But because both of them want to maximize progress, they coordinate to quickly go take over this human-driven car.
Yeah, I understand. But in reality, the actual space is much richer than that. You can fine-tune way more.
Yes, that's true. We just looked at a simple action space, velocity over at every time instance over the planning horizon. yeah, so the environment state in this case was this human-driven car, which we assume we don't know its dynamics, but we can learn it based on data. Okay, so it's just one example, but there are many. Of course, I believe that looking at this problem as a coordination and multi-agent has a lot of potential, but we are really actually trying to understand what's the best way to do this. And this was one recent approach, and we are sort of going further with these approaches, both in terms of theory and in terms of applications to human to robot or human robot interactions. So let me just conclude. So control theory is about, as I said, decision making for dynamic uncertain systems. As we increase automation, we have to manage increased uncertainties that either come from using our robots in new or unexplored domains, or from the interactions that arise between the robots and humans. And my lab works on focusing safety and also coordinating the interactions. And I presented a couple of ways to address these problems. This is sort of, we are continuing to address these problems. Our lab is growing. This is, I think the image quality is really poor. This is, sorry, but these are my group members. Actually, since then we have a new member, Tim who is here, but the picture is, we are constantly growing, so our picture is not yet on this figure. And we are also making a robotic platform to actually test these. So we have few robots running around and cameras, and there are some young members of the lab. This is also a bit of old pictures, and next time I can put my second son also in there. But we are working basically on extending these algorithms and verifying them on realistic test beds, and would be happy to talk to you about any of this theory or any of sort of experiment or test or ideas that you might have. And I want to thank you for your attention. And the work I presented today that is done with collaboration with my students, Ilnura, Giuseppe, my postdoc from when I was at UBC before coming here, Eugene Ann, and the master student, Kai, who was also at UBC and worked on the autonomous driving, like single player autonomous driving examples. And my collaborators, Ian Michel from UBC, and Jess Krause from ETH, and Tatiana Tatarenko at TU Darmstadt, and the funding. So thank you for your attention, and I'm happy to answer any further questions. Thank you.
Closing. So
Yes.
just some brief words of closing. So this was actually our last seminar before the summer break. So we hope to see you all soon again on 29th of August. We're looking forward to welcome Professor Surya Ganguly of Stanford University. And now for all those who came in person, there are some soft drinks after the talk. Okay, goodbye.
Thank you.